In this video, we're going to take a closer look at our small signal hybrid pi model. And so what we're going to be doing is sort of developing some parameters such that we can update this two-port network which we had at the end of the previous video. And so of course the idea is we can take that updated sort of equivalent BJT and place it into our AC equivalent circuit and then do our AC analysis. So let's start by looking at the input port, or our base emitter port on the left side. And so what we want to do is we're considering the relationship between our base and emitter side. And so we're going to use the same linear approximation that we talked about qualitatively and quantitatively before. So we're going to use our linear approximation, and specifically we're going to look at that qualitative part where we had the plot of our VBE voltage and our IB. So using the linear approximation of the plot, and so if you look in the notes, that's on page 4-3, what we had was that our small signal VBE is equal to IB times R pi. And so that's just another way to say that our slope was 1 over R pi. So writing that out formally, we can say we have 1 over R pi is the change in our base current with respect to the change in our base emitter voltage. And it's not just the change at any point along that curve. Remember, we said it's at some particular point, which is our Q point, which again is set by our DC analysis or our DC design, depending on which way you want to think about it. And so basically, again, this is just the slope at our Q point. So now what we can do is we can go back to our basic definition for our base current from the previous unit. So we can say this 1 over R pi is going to be equal to the partial derivative with respect to our VBE of our IB, which, as we've seen in a previous video, we can say that's IS divided by beta, exponential of our VBE divided by our thermal voltage VT. And again, we're sort of evaluating that at our Q point. All right. And so of course what we can see here is the only place we have dependence on that VBE is inside this exponential term. Derivative of an exponential is just the exponential itself. But then as we're doing the chain rule, we have to take the derivative of the argument of the exponential. And so in doing so, we're going to have a 1 over VT term come out. So we still have then the IS over beta, the exponential of our VBE, and note that this is our overall VBE, our DC and AC component, divided by VT, but we're evaluating that at the Q point. So because we're evaluating that at the Q point, that VBE value becomes VBEQ, and the corresponding IB value is our IBQ. So what we can say then is that our R pi, sort of just inverting that, is that our R pi is going to be equal to VT over IBQ. And so this is a similar relationship we had found before with a slightly different method. Now we know we're also going to be operating in the forward active mode for linear amplification, so we could also adjust this and have a slightly different form and say that R pi is equal to beta VT divided by ICQ. And so this is the first of a couple very important equations when we're creating our hybrid pi model in order to do our small signal analysis. And so this R pi is called our diffusion resistance, or sometimes we'll also call it the base emitter input resistance. So this is our diffusion resistance slash base emitter input resistance. And you'll see it called both or one or the other, just sort of depending on who you're talking to or what the application is. Okay, so that's our input port. So now we want to turn our attention to our output port, which is our collector emitter port on the right of the figure shown here. So let's look at our collector emitter port. All right, and so we're going to do a sort of a similar thing we did with our IB and the slope of the curve here. So we're going to say, let's relate our small signal collector current, so lowercase I, lowercase c, to our small signal VBE on. So we have then the partial derivative of our overall collector current, so lowercase I, capital C, with respect to our overall base emitter voltage evaluated at our Q point times our VBE. So again, we're trying to relate and so let me make that a little clearer that that's an E and not a C. So we're trying to relate our small signal collector current to our small signal base emitter voltage, and we're doing that by looking at the slope of the line at the Q point. And again, that's going to be a linear approximation. All right, so what we can say, and so one other thing I want to note too is initially here we're going to neglect the early effect. We're going to come back in a later video and we're going to see what that does to our model, but for the time being we're just going to neglect that. So we can say that our small signal collector current IC is then equal to the partial derivative with respect to our VBE, and we're just going to use the equation we had for our IC in the previous unit. So it's the same as the equation for IB above, we just don't have that 1 over beta factor, so IS exponential VBE over VT, and that is going to be evaluated at our Q point, and of course that's going to be multiplied by our AC VBE. So same basic idea here. As we're taking this derivative, we only have the dependence here. Derivative of an exponential is the exponential. Chain rule gives us a 1 over VT out front. So actually let me bring this down to this line here so we have more space. So we have this 1 over VT out front, and then we have our IS exponential of VBE divided by VT, and again we're evaluating that at the Q point, and that's multiplied by our small signal VBE. So similar to what we did with our base current, we can say, well, if we're evaluating that at the Q point, that's going to be VBEQ, which corresponds to ICQ. So now what we have is our small signal collector current is equal to ICQ divided by VT times our small signal base emitter voltage. And so we're going to create another parameter here, and we're going to say this is equal to GM times VBE. And so of course GM, sort of looking at those two equations, is just going to be ICQ over VT. And so this is the second important equation in our hybrid pi model. And so this is called our small signal transconductance. So small signal transconductance. Okay, so one thing to note about the relationship between our R pi and our GM, which can come in handy as we're deriving things later on, is we can say our R pi GM is equal to, so our R pi above, if we use the second expression, we had beta VT over ICQ, and then right there above we can see that our GM is ICQ over VT, and what we notice is that the ICQs and the VTs cancel out, and we're left with our R pi times GM is just equal to beta. And so one thing we've not mentioned previously is that sometimes we can say we have a different beta value, whether we're looking at AC analysis or DC analysis, but for the purposes of this class, we're going to assume that we have the same beta for AC and DC analysis. So we're assuming AC and DC beta values are the same. And again, not necessarily always the case, but we're just sort of making an ideal assumption here to make our analysis a little bit easier. Okay, so now that we have this information about our input and our output network, what we want to do is we want to come back and we want to update this two-port network. So let's go ahead and write that. So updated two-port network. So we get something that looks like this. And so I've sort of already got the framework here, but you can see we've got our three terminals, our base on the left, our emitter on the bottom, and our collector on the right. And so between our base and emitter, we have an equivalent resistance, which as we saw above is just going to be our diffusion resistance, R pi, or we can see why it gets its other name, our input resistance, looking into that base emitter junction. So we can call that voltage across that junction VBE. So again, everything's small signal here, so these should be AC values only. And of course, we have a base current which is coming into our base if we're talking about an NPN transistor. Now over here on the collector side, we have some current, which is our collector current. So I can write our small signal collector current here. And looking at this equation here, we said that collector current is equal to GM times VBE. So I've written a dependent source here, which is GM times our small signal base emitter voltage. And then of course we have the two base and collector currents coming down to this bottom node and summing to give us our overall emitter current. And again, all of these are small signal values. And so just like we had before, we can define our VBE voltage. And so I've actually already got that one written. So that's between our base and emitter. And we can define our VCE voltage as well. So there are a couple alternate terms that we can use. So sometimes instead of seeing VBE, what we'll see, and so let me use blue to distinguish these. So sometimes you'll see this voltage called V pi. And so accordingly, this would then become GM V pi. We also know we have the relationship in the forward active mode that IC is equal to beta IB. So oftentimes you'll also see this dependent current source labeled as beta times that small signal base current IB. So again, just a little bit of versatility in notation. Nothing is changing with the underlying circuit. You'll notice, particularly with this V pi here, I've used phasor notation. And so a lot of times with this AC small signal analysis, you will see phasor notation as well. Whether you want to use phasor notation or the AC sort of small signal notation is up to you. Both are appropriate. So you might also see, for instance, VBE, phasor notation for our base emitter voltage. So now that we've got our updated BJT model based on our hybrid pi model, the next step would be to go back to our AC equivalent circuit and replace our BJT with this model. So our next step for our AC analysis is to replace the BJT with our hybrid pi model. And what that's going to give us is our sort of full AC equivalent circuit. So to create our AC equivalent circuit. And so we're going to look at an example in the next video of how we do that and what that looks like. But basically, sort of thinking ahead, now we've simplified this so we only have components that we're a little more familiar with. So we have a resistor, we have a dependent current source. So these are all things that we've been dealing with in the past. So that's going to make the analysis of our AC circuit much simpler.